In Section 7.5, we'll pick up our fourth gas law, which connects trends in volume and moles of gas when pressure, volume, and temperature are held constant. We'll do this by exploring the concepts behind the law and working through some examples. Let's begin. Consider two gas samples that are identical. That is, they have the same pressure, volume, temperature, and number of particles. If these two samples are combined, P and T do not change, but V and the number of particles have doubled. Avogadro's law states that when the pressure and temperature are held constant, the volume of a sample of gas and the number of moles in the sample are directly proportional. We can express this direct relationship as the ratio of the volume and number of moles of gas under one set of conditions as being equal to the ratio of the volume and moles of that same gas under a second set of conditions where the pressure and temperature are held constant. Let's apply this law to an example problem. Suppose we have 22 grams of gas-phase carbon dioxide occupying 15.3 liters, and we want to see what the new volume will be if we add 15 grams of carbon dioxide. First, we'll tabulate the data and get the masses converted to moles of carbon dioxide gas. Since the moles are increasing, we know that V2 will be greater than V1. Rearranging Avogadro's law to isolate V2, we get V2 equals V1 times N2 divided by N1. Plugging in the data, we get V2 equals 15.3 liters times 0.841 moles divided by 0.500 moles equals 25.7 liters. Here's one for you to try. Suppose 0.329 moles of oxygen gas occupy 0.944 liters. Without changing the temperature or the pressure, we add enough oxygen that the volume increases to 2.47 liters. We could ask this question in two ways. We could ask you to identify the number of moles of gas added, or we can ask the total number of moles of gas in the sample. Let's rearrange Avogadro's law to solve for N2 by cross-multiplying and dividing before we drop the values into the equation. Solving, we get N2 equals 2.47 liters times 0.329 moles divided by 0.944 liters equals 0.861 moles to three significant figures. That's the total number of moles of gas in the sample under the second set of conditions. The moles of gas added are 0.861 moles minus the original 0.329 moles we started with to give us 0.532 moles of oxygen gas added to the sample to go from 0.944 liters to 2.47 liters. This section includes just one parting thought from the authors.